Hey guys, Mr. Backerberg here. In this video we're going to look at inverses of exponential functions. So as we're thinking about exponential functions, if we looked at some general f of x equals b to the x, its graph would look approximately something like that. And we know that every graph that passes the horizontal line test has an inverse. So exponential functions have inverses. And the inverse of an exponential function is a logarithmic function. Now we typically do a lot of changing back and forth between logarithmic form and exponential form as a way to try to make logarithms make more sense. So if we have something written in logarithmic form, we're going to have something written as y equals log base b of x. And we can actually take that and switch that into an exponential function. And what we do is we grab the base of the logarithm, that becomes the base of our exponential. This y value goes up as the power on that base, and the x value is what our exponential function is going to equal. So we can switch back and forth between this logarithmic form and this exponential form. Sometimes we take logarithms and turn them into exponentials. Sometimes we take exponentials and turn them into logarithms. But this is how we're going to switch back and forth between the two. So in this first example, we're going to look at evaluating some logarithms by turning them into exponential functions. So say we wanted to look at something like log base 2 of 8. And that's going to equal some unknown value. Then if we take that and turn that into an exponential function, what I'm going to do is I'm going to take the base of my logarithm, that becomes the base of my exponential. The answer is the power, and this value that we're evaluating, so this 8 in here, becomes the answer to our exponential function. So now we're trying to think, what power do I have to put on 2 to get 8? And the answer is 3, because 2 cubed equals 8. So the 3 power is the answer to my logarithm. So log base 2 of 8 is equal to 3. So let's look at another example in here. If we wanted to do log base 3 of the square root of 3 and figure out what that's equal to, what I would do is I would take that base of 3, I would put my unknown power on the 3, and that's going to equal the square root of 3. So I have to think about what power would I put on this 3 to get the square root. So what power means the same thing as a square root? And that's going to be 3 to the 1/2 power, because a 1/2 power means the same thing as a square root. So log base 3 of root 3 equals 1/2. Or if we looked at another example in here where we had log base 5 of 1 over 25 equals some unknown value, we would be thinking to ourselves, 5 to what power gives me 1 over 25 as the answer? And it's going to be 5 to the negative second power, because with that negative second power I would really write that as 1 over 5 squared, and 1 over 5 squared is 1 over 25. So the answer to this logarithm, log base 5 of 1 over 25, is negative 2. Now using that relationship between logarithmic and exponential functions allow us to come up with some properties that'll save us some time when we're doing some problem solving. But we do have to include a couple restrictions. So number one, our b value has to be greater than 0. But also our b value cannot be 1, because if you're dealing with a base of 1, then any power you put on it, you're always going to get 1 as an answer. So if we're looking at log base b of 1, and we're trying to figure out what that answer is, well, we can think about taking b, putting our unknown power on it, and getting 1 as our answer. So what power can we put on any number and always get 1 as the answer? And that power is 0. So log base b of 1 is always 0, because if you put a 0 power on any base, the answer you get is 1. Now another property that we can look at is if we have log base b of b, and we're trying to figure out what power we would put on that. So what power do we put on a base to get the exact same answer? That's going to be a first power, because b to the first power is still b. A first power doesn't change that b value at all. A couple more properties I'm going to throw your way. Same exact restrictions on b. b needs to be greater than 0 and b cannot be 1, but I'm going to throw a couple extra restrictions on here because we're going to have a couple more variables show up. When we look at our x values in these properties, our x values need to be greater than 0. But when we look at our y values in these properties, these can be any real number. So the first one I want to look at is log base b of b to the y power. And we're trying to figure out what that's going to equal. Well, if we take that and write that in exponential form, this would be b to some power equals b to the y power. And as we're looking at this, what power of b would we put on b to get b to the y power? Well, that power would have to be exactly the same in order for these to be equal to each other. So this power would have to be y. So log base b of b to the y is equal to y. And the reason is because logarithms and exponentials are inverses of each other. Just like addition and subtraction are inverses of each other, they undo each other. So when we look at log base b of b, we can think about this log base b canceling out with this exponential base b and just leaving us with this y value as the answer. Now, similar things happen if we're looking at an exponential function. So let's say we had b, but we're raising it to the power of log base b of x. And we're trying to figure out what that's going to equal. Well, we could actually rewrite this in logarithmic form. So this would become log base b of some unknown value is going to equal log base b of x. Well, in order for these two logarithms to be equal to each other, then this value that we're evaluating needs to be the same. So this unknown value would need to be x. So b to the power of log base b of x is going to equal x. And again, it's because exponentials and logarithms are inverses of each other. So having this b exponential along with this log base b, they're canceling each other out and just leaving us with this x value as the answer. So let's revisit a couple of those examples that we looked at earlier. Earlier on, we tried to look at log base 2 of 8. And we had some unknown value, and we switched this into an exponential function and made it say 2 to what power equals 8. And we said that answer was going to be 3. But there's actually another way that we could look at this. So if we're evaluating log base 2 of 8, what I'm actually going to do is rewrite the 8. I can rewrite that 8 as 2 cubed. And then we've got a log base 2 and an exponential with a base 2. So we can think about those canceling each other out and just leaving us with this power as the answer. Or if we wanted to look at that example where we had log base 3 of the square root of 3, I can rewrite that square root of 3 as being 3 to the 1/2 power. And then log base 3 and this exponential base 3, they're going to cancel each other out and just leave us with that 1/2 power as our answer. That's going to be it for this video. Thanks for watching.